The first thermonuclear detonations exceeded the yield of early atomic bombs by a factor of 20, achieving that explosive power with significantly lower mass. During early Cold War operations, militaries relied on a safety protocol known as separables. A capsule of fissile material was kept physically separate from the high explosive bomb body, often requiring manual assembly in the cargo bay of an aircraft en route to a target. This meant that an accidental crash could not trigger a nuclear explosion. But as the risk of an unannounced first strike grew, the time required to assemble these weapons mid-flight became a strategic liability. Meeting deployment criteria meant satisfying conflicting goals. Warheads had to be compact enough to fit on ballistic missiles and ready for immediate launch, while increasing explosive yield and maintaining absolute safety. The specific configuration that addressed these constraints was outlined in 1951 by physicists Edward Teller and Stanislaw Ulam. They proposed a staged architecture. Instead of a single explosive event, their design uses the energy from a smaller fission primary stage to trigger a physically separate fusion secondary stage. By condensing multiple explosive stages into a single stable mechanism, the Teller-Ulam design provided the yields and readiness levels required to sustain the policy of mutual assured destruction. The sequence begins at the top of the warhead. Conventional explosives detonate precisely, driving a shockwave inward to crush the primary fissile core. Under this immense pressure, the core reaches supercriticality, initiating a boosted fission chain reaction instantly. This fissioning primary produces 4 outputs: expanding gases, superheated plasma, high-energy neutrons, and a massive burst of X-rays. The whole ROM acts as a containment vessel, temporarily trapping this intense flood of X-rays and reflecting the radiation inward. The void between the primary and the secondary stages is filled with an interstage material, historically composed of polystyrene foam or a substance known as fog bank. As the wave of X-rays strikes this foam, the material absorbs the radiation and is instantly converted into a highly energized plasma. In a thermonuclear weapon, the primary stage is not the source of the main explosion. Its function is to serve as a massive X-ray engine to power the ignition of the secondary stage. This presents a specific physics challenge. How exactly does the X-ray energy crossing the interstage physically compress the separate fusion secondary? Historically, 3 different mechanisms have been debated in public domain physics: pure photon radiation pressure, foam plasma pressure, and tamper-pusher ablation. This chart displays the calculated pressures for the IV mic test device. The first row shows pure photon radiation pressure, which generates 7.3 terapascals. While 7.3 terapascals represents enormous force, it is insufficient to crush a solid metal cylinder. The second mechanism is expanding foam plasma, yielding 35 terapascals. However, compressing the secondary fusion fuel requires a threshold of over 500 terapascals. Neither radiation photons nor foam plasma reach that limit. The only physical mechanism that produces sufficient force is tamper-pusher ablation, generating an estimated 530 terapascals of inward pressure. Ablation is a mathematical necessity. It is the only mechanism capable of delivering the hundreds of terapascals of force required for thermonuclear ignition. At the microsecond scale, the intense X-ray flux is immediately absorbed by the outer skin of the heavy uranium-238 tamper surrounding the secondary stage. This absorption causes an extreme phase change. The outer layer heats to several million degrees, causing the solid metal to instantly vaporize and boil off. The vaporized material blasts outward from the surface at a velocity of approximately 290 kilometers per second. Applying Newtonian conservation of momentum, this massive outward ejection of matter dictates an equal and opposite physical reaction. The unvaporized inner mass of the tamper recoils inward at roughly 400 kilometers per second, violently crushing the core. Leveraging this extreme vaporization to drive a hypervelocity inward recoil allows the weapon to bypass the physical limits of standard chemical implosion. This implosion zeroes in on the absolute center of the secondary, compressing a hollow pillar of plutonium-239 known as the spark plug until it fissions. This internal fission explosion acts as a central heat source, warming the surrounding layer of lithium-6 deuteride fusion fuel from the inside out. Simultaneously, neutrons from the spark plug bombard the lithium-6 nuclei, splitting them into tritium and an alpha particle. The extreme internal heat forces this tritium to fuse with the deuterium. This fusion reaction releases a massive burst of high-energy 14 mega-electron-volt neutrons. These fusion neutrons slam directly into the dense, highly compressed uranium-238 tamper while it is still recoiling inward. While natural uranium-238 cannot sustain a chain reaction from slow neutrons, it undergoes massive fast fission when struck by neutrons moving at this high energy level. This final uranium fission event accounts for approximately half of the weapon's total explosive yield and generates the vast majority of the radioactive fallout. Consequently, the common term hydrogen bomb is misleading. The fusion fuel primarily serves as a high-speed neutron generator, while uranium-238 fast fission provides the actual engine of destruction. In practice, these events execute in a fraction of a microsecond, functioning as a single, fluid reaction. Chemical explosives trigger a fission primary, which emits X-rays that cause ablation. That ablation compresses the secondary to trigger fusion, and those fusion neutrons ignite the final fast fission explosion. By integrating these stages into one stable architecture, engineers secured the high-yield, instantly deployable weapons required for modern strategic deterrence. The development of the Teller-Ulam design provided a technical solution to these requirements, establishing the physical basis for the era of mutual assured destruction.